Hello everyone. This video is for Unit 2 Case Connection. Sorry about that. Just had to readjust my screen. So, for Unit 2 Case Connection, I decided to do Case 2. And for Case 2, the issue was the above brain MRI shows a large glioblastoma tumor with areas of necrosis within the tumor. And then it showed a PET scan of the individual and how that tumor was taking in glucose. So use the following series of questions to determine how/if glucose uptake differs in the tumor when compared to the surrounding tissues. So the first thing that I will address in this video is in normal tissue, how is glucose uptake regulated in the following tissues: liver, skeletal muscle, brain, and adipose. So the liver utilizes glucose transporter GLUT2 for rapid uptake or release of glucose in order to regulate glucose levels. Glucose is phosphorylated to glucose 6-phosphate, which is catalyzed by glucokinase in the liver. Phosphofructokinase may be inhibited by ATP concentrations, and pyruvate kinase are the other enzymes that help regulate glycolysis in the liver. For skeletal muscle, glucose needs to be transported into the cells via GLUT4. Then it is phosphorylated by hexokinase. Glucose can't just be readily uptaken by skeletal muscle. It absolutely needs a transporter. And then it's phosphorylated by hexokinase compared to glucokinase in the liver. So limiting any of these enzymes would limit the uptake of glucose, and increasing the activity would increase the usage of glucose for skeletal muscle. The liver and skeletal muscle also use fructose 1,6 biphosphatase, which determines whether a tissue can synthesize glucose or glycogen from pyruvate. Hormones such as epinephrine and glucagon will inhibit glycolysis and activate gluconeogenesis in the liver by increasing the concentration of CAMP. Then on to the brain. The brain uses the transporter GLUT1 and 3 in order to receive glucose. The brain will use an isoform of hexokinase to phosphorylate glucose to glucose 6-phosphate. This step is feedback inhibited by the product, which helps regulate the process. Specialized centers in the brain, such as POMC and AGRP neurons, sense glucose levels for the nervous system, and that is what regulates the glucose metabolism via the vagal nerve system, vagal nerve, which also regulates how much glucose is being transported into the brain. Adipose tissue uses transporter GLUT4, just like skeletal muscle. Insulin, which is released by the pancreas, increases glucose uptake by adipose tissue in order to regulate blood glucose levels. When blood glucose is low, hormones such as glucagon will increase adipose tissue's release of glucose to increase the blood glucose levels. So on to the next question. How does glucose uptake in normal tissue compare to glucose uptake by tumor cells in the above image, and why would this be advantageous to the invasive tumor? For fast-growing cancer cells, glycolysis is increased to produce a high amount of pyruvate, which is turned into a high amount of lactate. So the cancer cells have a much higher glucose uptake compared to normal tissues. This process creates an acidic environment for the tumor as well. The cancer cells have altered their metabolism in order to have glycolysis occur rapidly, in order to reproduce quickly and create their acidic environment, which is very beneficial for the cancer cells. Fatty acid synthesis and glutaminolysis also increases to support the tumor's growth. The tumor cells need to replicate quickly and they desire that acidic environment. So an increase in glucose uptake is very advantageous to the tumor in more ways than one. Next question, what modifications may have occurred in cancer cells to alter glucose uptake as predicted above? It is believed that what is called the Warburg effect occurs, which gives tumor cells the ability to increase their glucose uptake, aerobic glycolysis, and lactate fermentation, which is what I mentioned before about creating that acidic environment by having such a high production of lactate, which in turn creates lactic acid, which then in turn creates that acidic environment that's so beneficial for the tumor. The Warburg effect is when the cancer cells only partially break down the glucose that is taken in at high amounts. And by that, I mean glycolysis occurs, but the next step, which would typically be oxidation phosphorylation, does not happen, which means the further breakdown is pyruvate being turned into lactate. The system seems inefficient, but not only do the cells get their high level of glucose to function and replicate, it also creates that acidic environment. The modification is to the mitochondria. That is what is assumed here due to those certain processes that are being altered, and those certain processes occur in the mitochondria of the cells. It is believed that the modifications to the mitochondria causes the tumor cells to have aerobic glycolysis and to not use oxidation phosphorylation. The tumor cells also cause glycolic enzymes such as GLUT1, lactate dehydrogenase, pyruvate kinase, and lactate exporter to become unregulated, which a couple of those were mentioned before when I was talking about how regular tissues regulate glucose uptake, and the tumor cells utilize that all of those regulators that normal tissues utilize, but in a bad way. So they make those regulators go out of whack. And by that, I mean they typically have the GLUT1 transporter, the pyruvate kinase, and the lactate exporter. They make their activity much higher than typical, unregulated. So the systems that would typically stop those transporters and enzymes from overproducing, from overdoing their job, the cancer cells stop that. So they encourage them to keep doing their job, which is good for the cancer cells. And let me see. Yep, and then all of this leads to increased glycolic flux, and pyruvate cannot enter into oxidative phosphorylation. Like I said before, the pyruvate is then turned into lactate, which is then used to create the acidic environment. And that is it for case 2. And on my written up script, I have my references, and you can see in the script where I used those references for all of my information that I'm talking about today. So on to case 3. So this is the second case that I decided to talk about today. So in case 3, a 5-year-old boy was brought to the pediatrician's office for an annual visit. The mother reports he has been a sickly infant and often appears drowsy. She also has concerns over her son's persistent thirst and frequent urination. Blood samples are taken for insulin measurements at time 0 and 1 hour after a glucose loading test. So the questions are, what is this information likely to suggest about the underlying biochemical basis for the patient's symptoms? This information suggests that the patient is experiencing symptoms from type 1 diabetes or diabetic mellitus. This type 1 diabetes is when the body cannot produce enough insulin on its own, typically due to damaged insulin producing pancreatic cells, and those are the beta islet cells of the pancreas. Insulin is what frequently controls the level of glucose in the blood system. When blood sugar is too high, insulin is produced and released. Lacking the ability to produce insulin, the patient's insulin levels will be low at their baseline, and when they're given a loading dose of glucose, it will still be low because that loading dose of glucose will not change the fact that the patient is lacking the normal ability to produce insulin to respond properly to that loading dose of glucose. And then the symptoms of increased thirst, frequent urination, and drowsiness are common signs and symptoms of type 1 diabetes. What would you predict the patient's fasted blood glucose levels to be given his current condition? I would predict that it'd be the patient's insulin level would be below normal range, since it is below the normal range for every other test, and that he is most likely diabetic. Since the insulin levels would be low, the fasting glucose level would be higher than normal because can't produce the normal amount of insulin, so there would be more glucose just kind of free floating in the blood than you would typically see. Normally the insulin would be released to take care of that high level of glucose in the blood. There would be not enough insulin produced to properly take care of glucose in the blood, which will cause the blood glucose level, even at fasting, to be higher than normal. Then list 2 regulatory enzymes that are likely to be active in the individual's current condition. Glucose 6-phosphate and fructose 1,6-bisphosphate would be 2 regulatory enzymes at work. Both play vital roles in glucose utilization. A study published in 2006, which will be my references, showed that inhibition of fructose 1,6-bisphosphate in diabetic rats actually helped reduce the production of glucose, which in turn reduced the blood glucose level that would typically be quite high in diabetic patients, and which would typically be quite high in these diabetic rats that were tested, but they found that the blood glucose level dropped due to inhibiting that fructose 1,6-biphosphate. Because those 2 enzymes that were mentioned, they're still at work, even though insulin isn't available at normal levels to then kind of remove that glucose in the blood. They're still going to be at work because the patient is probably still eating, they're still consuming sugar, so the body is still going to have the processes that utilize glucose 6-phosphate and fructose 1,6-biphosphate working, even though that you then don't have the regulatory insulin to help kind of balance that out. So you would still see those 2 enzymes working in the system. All right, thank you for listening. I hope you have a good night.